right? Banana slicer. What's wrong? Spoons are good. Okay, so, please. I'll tell you about a few random things as usual, and then we'll talk. I'm going to try and clean up this contagion thing because I know. We talked about it a lot, but I have the right story in the right place, and it's where it should have been like 7 lectures ago, but we'll get it. And then I'll tell you about a weird kind of contagion, chaotic contagion on networks, which is basically just a dream collusion of various disciplines. It's a good example of where you take something, take a sort of a natural, it's a model of hipsterism, if you like, or fashion, and you abstract it, and then you play with it a little bit, and now you're off in applied math, like, ooh, I found a fun thing. And it took me about 10 years to actually finish it, because I found all these fun things, but they lost touch with reality. But it's super cool. It has some really weird behavior in it, so we'll talk about that. Okay, so I have a couple of things. I want to mention this. This is a very solemn thing for Australians and New Zealanders. Anzac Day, it's April 25th, and commemorates a disaster, actually. And it's one of the sort of few, I believe there aren't many around the world where the main military, the day of military, observance of a military action is of a calamity, and it's Australian and New Zealanders largely being essentially annihilated on the shores of Gallipoli. So it was against the Ottoman Empire, right? This is a long time ago, and the last few veterans, passed away in the last 10 years. But it's a big deal to Australia. There's Gallipoli, of course, so it's very famous in our history. There's it's a long time ago, but there's a movie called Gallipoli. Maybe you've vaguely heard of it. It's an early film with Mel Gibson in it, right? So Mel Gibson was evolved in lots of different ways, but he's actually from upstate New York, which is odd. His father was from upstate, and they moved to Australia when he was young, and he ended up going through Australia's main acting school. Of course, Mad Max, right? Right? Mel Gibson. But this other film is about Gallipoli, and essentially, the English are in charge. This is the law we have, and land on the wrong beach using tourist maps apparently that were just wrong, and just try to charge being sent up, and just the Turks would just annihilate Australians. So that was yesterday. It is it's our sort of our main day, and it's kind of why we like sport. Yeah. Okay, so other things have just appeared. So Simon Tadeo, you may have seen, you may have come to his talk last year. He was here talking about the evolution of law, the legal system in England through documents from the Old Bailey. How things went through certain kinds of punishment, what became defined as punishment. So the way this is titled, of course, is that the Wikipedia, the editorial structure is this huge bureaucratic thing. It doesn't look very different. The claim is it doesn't look very different from any large organization at all. Of course, it's still, there are norms, right? They're the rules. There are these emergent norms over time, and they list a few, right? So you've got to cite everything. There's no yelling. You're not allowed to type in capital letter. There are all these little, so be nice to each other. It's encoded in very explicit laws, and then it becomes lifted into more general ones. And I guess the claim is that we've known this, I suppose. There are very few. There are very few central editors. Get these kind of inscrutable network pictures as usual. Very few editors who really dominate the thing, and then there are a lot of people who turn up and they edit the one thing they know about, or try to clean up. So there are a lot of editor wars. I guess the claim, so a lot of people know that, but the interesting thing is that the norms that have evolved, then you kind of end up with people centering around these different norms, right? So be nice to each other, be fair and balanced, or be balanced, be neutral, right? Neutral is the term. And they end up kind of fighting against each other a little bit, because they, if you really adhere to one of them, it can sometimes force, that norm is of lesser importance to you. It's a tier of norms. Yeah. Anyway, so it's Simon, he seems to have got a lot of press for this. He's got a strong, I want to find this one. He's got a very strong statement here. Where is it? Sorry. That's pretty awesome. Yeah. Every single action that anybody did has been tagged to the second. The resolution of the data is so good, we are like gods. It's a little strong, came off a little strong. Gods who just watch things, which, anyway, all right. That's an interesting piece of work. You know, this is an organizational story, right? This is a very recent kind of organization made possible by the web, the internet, which you now is a small I internet, right? That's the AP style has changed, so you must spell it now with a lowercase I. I just want to tell you that. That's important. There's another one here, yeah. Okay, that's a different piece, and that's about, yeah, this is the small number of, right? It's a power law size distribution. You may have heard of those things. So it's you're right. So it's all ended up being this, right? Yeah. And I mean, people take over domains and then they're in charge of that, and they have things that tell them when a page has been changed and all. So you can exert this power, I guess. But you only have so much time still. So maybe they have, you have a team around you eventually. Yeah, anyway, interesting thing. This I heard it was on a podcast I listened to. I don't know I can't remember what it was, but I was just looking this up. So they were talking about organizational collapse, right? So one kind of organizational collapse, which we like to talk about in science fiction, is, an EMP, electromagnetic pulse. It's all gone, and I guess that TV series Revolution, is that what it was called? Does anyone know about this? The lights went out. Essentially, it turned out to be nanobots or something ridiculous. But anyway, so you plunged into industrialization. So what happens to the world? So there's, I can't remember this. I think it's in the South. There's a library where they've been collecting books on how to farm, right, with horses and so there's and we have the seed. The big seed storage thing in Norway, perhaps, is it? It's in Scandinavia somewhere. People are trying to, so it's robust under extreme failure, right? I think the upshot of this is, one of the people who's been curating this, reading a lot of books about how to do stuff when you're in trouble, and the upshot is you don't want to live in that period of time. It would be tough and not fun. Okay, anyway, so there's that. So survival library, good. Tweets, there have been tweets. Oh, this are more tarot cards. Yes, I have some more fun tarot cards. This one says limit of organizations. That's the robust yet fragile thing, got chomped, right? The overcoming of catastrophe. Troubles ill-formed, this is about solving a puzzle. So you've got the generalists up here, they know the big picture, but they don't know any details, and so they can always, this is the CEO trick, right, of saying, I didn't know that they were doing that. Sure, buddy. The networks-of-many-ilks. So this is something I want to talk a little bit more about today. This is the mixed flavors of edges. It's good stuff. This is really very nice. And did I do this? Oh yeah, ratio of gain, I didn't have that. That's pretty straightforward. And that one I tweeted twice, I guess. Chaos-of-fettered-contagion. That's what we'll talk about today. Yes. Fettered is a fun word. I want to mention this just here. So we have computer associates. We have a new fellowship that they will support. It's a 2-year piece, and it's for our new masters in computer complex systems and data science. So that's exciting, and we of course have the Fox. So hopefully that is something that grows, but we need that person to apply, and we will have them up and running in the fall, hopefully. So it's all going to be very quick. These are other things, but yes?
Do you have any applicants for that program? Is there anybody?
So advertising started very late.
Yeah, well, right.
That's a problem. So next year hopefully will be really good. But we're getting some, and we're getting very nice comments from people, because there's a uniqueness to what we do. So, even two things, I guess. Just the merging of complex systems and data science is appealing to people because data science often goes into data analytics. It's often sort of associated with business or something kind of like that. And complex systems, people can think of that as sort of the 90s version, which was data-free and theory-full, right? So Basically, it just means we're doing science. But yeah. Maybe I mentioned this, Jake Williams, who's a alum of these courses in Story Lab, and he did his undergrad here and then sort of evolved and realized that he could actually do a PhD and crushed it. He's now accepted a position at Drexel, so that's really exciting. Yeah, all the video replays, those things are up. And that's a new paper of ours. Emily Cody also went through pucks on how the media coverage, so looking at newspapers, changed before and after these two particular catastrophic hurricanes, Katrina and Sandy. And after Sandy, it's much more about climate change. After Katrina, the dominant thing is about energy markets, money. Okay. We're doing all right? What else have I got to tell you? This is totally random. I just thought of this before. This is pretty funny. I was telling someone this the other day. It took me a lot. So when you move between countries, right, you notice some things are completely obvious. If you got a different language, you notice all these things. I mean, if you move between countries that people drive in a different direction, for example, that is an important thing to take note of. And it sort of blows your mind. It's really hard to, you've got like childhood jingles of look to the right, look to the left, look to the right again. I mean, I could sing one for you. It'd be very bad. But, wrong. It's a bad algorithm. It's a bad algorithm. That's going to be the end of you. And what happens is after a while you get good at it, but then when you turn around a corner, you forget. So it's all fine, and then, yeah. Anyway, little details like whether something like Mr. has a period after it or not. There's some weird things that differ between, say, UK and the US. But this is really weird, right? So it took me a long time. I mean, I'm married to an American. Generally speaking, I guess in the US, people cut things up and then you swap and use a fork, right? Yeah, and then you're good. Got it all set up, right? So in the UK and Europe and Australia, it's the fork is doing this thing over in the left hand, right? There's none of this changing. So this traces it back. It turns out that an old student of ours, married to a Swiss woman, ended up in Switzerland, and his new family, his extended family, ridiculed him for the way. This is how I found out about it, and he was telling me about this, and I'm like, what? That's not true. And then, I watch my wife eat, and I'm like, oh my God. Anyway, so it turns out that the French did this as a mannerism, as an aristocratic, affectation that they sort of built on, because you have algorithms for eating so that you don't die. There's, washing hands or whatever and passing things and being nice, and then it gets out of control, right? Then you start to do all sorts of things. But they started to do this because it was, they're wearing funny clothes and the whole thing. And then it disappears from them. They're like, what? It's gone. But somehow it got tied to the US and then it just sort of got baked in. So it's just a really weird thing. Anyway, that was just so if Europeans say whatever, you can tell them to shut up, just shut up, because, you guys do this, this, and this, and this. But it's weird. That's a weird thing. Anyway, sorry. Yes.
Yeah, there was an interesting thing in World War II. A couple of American spies were caught because
they would do that.
Germans sat them down and saw which fork they picked up, or which hand they picked up the fork with.
Ouch. It's something you don't notice. And there's also, Inglourious Bastards, right? Inglourious Bastards? Well, which one is which one? Which is correct if you're from the, yeah, so which one gets you shot by Germans? I guess is the way to frame it. This is bad. That's bad. That's like an Englishman's thing. But that's a bit hard to do. 3, okay. Anyway, you got to really concentrate, obviously, so. That was a nice detail. Nice detail. Good. Jeez. Okay. Algorithms, right? These are algorithms. This is algorithms for eating things, yeah? So years ago, this is just random, but years ago I was camping with my wife. We're up in the edge of Maine and New Hampshire, and I've managed to leave a large portion of the food at home on the couch, which was where we found it later on. A bag containing food and various other aspects. So we lived on rice for a couple of days, but not so great. But the first, realized this, and we're overcoming our little disaster, and then I look around and I realize there are sticks everywhere, right? So you've got chopsticks, we're good, right? We've got chopsticks and with things to stir with. So there's this moment where I think I'm a genius for realizing, I could use the things around me, and then I think, like whatever it is, 6,000 years ago, someone else did that. So it quickly got, slammed back into the box of being self-impressed. So, yeah, who didn't know what chopsticks were, of course. Yeah, much harder, right? Anyway, fun things. Tarot cards, here we are. So good, right, added these guys, and things did not explode. Yeah, I'll get all these things to work eventually in other ways, but that's good. And there was a fun little, let me find this for you. Super wrong. This is really silly. Where is it? Yes. So matrixology, which is my linear algebra course, now has its own little set of, these are small ones. These are the small versions. So yeah, this is what I did last time, right? They were themed by games. There were 10 things, and I had 10 games mostly from the golden age of video games. So the first one was Pong, which is like 72, and then Zork, which is just command line stuff, awesome. And that's actually 77 or something, I think. And then there's Space Invaders, which actually comes before Asteroids, which is hard to comprehend. And then, you get these good things. This one of my favorite games, Galaga, love it. Pac-Man, Pitfall, Atari, very good, excellent. Pong, there's good old Pong. And Q*bert, poor old Q*bert, sad Q*bert, who's, right, in Wreck-It Ralph is a homeless game by that point. That was tough to watch. Tetris is 1984, actually, so it's so simple, right? But it's beyond that. When I first arrived at MIT, the Russian guy who had invented it was living in the Media Lab by that point, so hugely famous for doing this. I don't think I clued into this, and I know I showed you the Tetris on the, but it's just little blobs of 4, right? That's what it is. Okay, anyway. There's really no need for that, but I did it. Okay, we're running out of things. Yeah, so I just wanted to, so we've got this piece here. If you want to share that with people, please do so. We have a fan over here. Amanda, she's great. Okay, good. And the rest is LaTeX madness. Okay, craziness. All right, I just want to clean this up, and then we'll talk about this madness of chaos on networks. So there's a first bit here where we were talking about these mixed networks, right? So they have undirected edges, which you can think of as bidirectional edges, probably the best way to think about it, and then directed ones. And we couldn't just randomly wire them all up because we wouldn't be able to control what we'd end up with. So, right. Okay, so, yeah, right. If you just had direct and you randomly wire up, you'll never get them, 2 directed ones. Yeah, so that was an important thing. So we figured out the condition for these things having contagion, having global spreading events, and then the game. So this next piece, and then I want to go back and clean up what we did with generating functions. I want to show you that it's all good. So I'm going to come back to that, but well, let me do it this way. Okay, good. Let me do it this way. I'm going to go to. This is good. I mean, I realize it's out of sorts and it should be out of order and it should be back here, and you should have seen it ages ago, but my brain is not strong enough. Okay. I don't know. All right, so here it is. So I'm going to quickly recapture a couple of things we talked about. This is really just basic contagion on random networks with arbitrary degree distributions, right? So really, this is a bedrock thing, and you've got to really know about that coming out of, say, a complex networks course. So we got to this story where we realized that there was, you had to have a global, a giant component of vulnerable nodes present in the system for this thing to take off. And it gets more complicated if you have groups and all sorts of things. Saw that in Pox already, but we're going to really get this right. And we'll do something where I'll show you the generating function stuff quickly again, but we'll do it in with a physical explanation, right? This is the way you really need to do it if you can. And we'll look at where we're just doing math, moving from one place to another. For instance, in that Gleason assignment now, assignment 10, you have to produce those C sub L's. That's just a math festival, right? You're just playing around with a little bit of math. Rearranging it, smooshing it into some other thing. right? Making a polynomial for yourself, because we're totally psyched about polynomials. Taylor expansions, great. But it's just a bit of, you're bashing around with math. It's not clear that you could say, here's the physics for this bit of algebra. Algebra is, no, right? Okay, it's the dead monk situation. All right, so we know this is true. And then we have on top of this that there's this probability of the thing spreading, and it's, well, you could start in this vulnerable component, or you could start outside of it, right? You could start with something that's connected to it. And I guess I could, I want to make sure I'm a bad person. Where is it? Sorry. Yep. Here's the key picture. Right? So this is our vulnerable component. All these nodes just take one hit, one of their friends turns on, they switch on. So if you started in here, just turn on one node, then all of this will turn on. Potentially, others will turn on that need 2 or more hits, and that's the Gleason work that gets you this. But we're interested in the seed situation. When is this thing going to explode? What, Achilles heel type situation. And then there's a triggering component around it, and that's ultimately the big. What's the probability this thing takes off? So you could have someone who has 100 friends out here. They're not vulnerables. No one would turn them on with just one hit, but they have connections in here, and they will start a fire. And that initial one could be in the final, right? They could be part of the final component, or not. So let me get this. Okay, so these are our stories, right? Fine, so we're trying to find this and this. And we had this crazy thing with generating functions. It's opaque, it's a nasty business. Oh, it's on the next page. God, I'm just, damn. Okay, I was trying to help myself, I failed. Right, so we had this kind of madness here, right? So this is the distribution of component sizes, right? The probability that you choose a node, a randomly chosen node, you find out what's the size, and you turn that one on. What's the size of the final spread from that node? And it had this nice thing. We use these 2 tricks, right? One is if you're just adding 1 for yourself, you just multiply an x, and then this is the die you roll. It says you draw a number from here, and that's how many times you roll this one. This is a cool story. And we realize that it's really always about edges. So you're going along an edge, you need to know how many other friends that edge has probabilistically, and that's the R distribution, right? Which probably has k other friends. So you get your k, and then you sample from how big those subcomponents are out there, right? Spreading through this edge. Add 1 for the first node that you hit, and so it's a recursive story. This is an opaque thing, for sure. Okay, so quickly we're gonna, and I'm sorry this is all out of order, but we're gonna do it. Okay, so it's node-based percolation. Then we had this story that if you have some distribution of thresholds, if we think about the threshold model, then we're worried in particular about this guy, right? What's the probability that a degree k node turns on when one of its friends is on? It doesn't have to be the threshold model, it could be anything, right? We could throw all this away and just specify this in some way. What's the chance that a degree k node gets switched on with one friend? Right. So we had this madness. This is for the threshold model. And I just want to sort of just quickly touch on it again. It's a tricky business. What's the probability that if you choose a node, right, so we're going to choose a node, that it's part of this is a subtle thing, it's part of a finite component of vulnerable nodes. The extra tricky part is the first one might not be vulnerable, right? So it could be excluded from this. So it could be a part of a component of size 0. And the problem with this approach as well, from an intuition standpoint, is that we always avoid the giant component. We calculate everything else, all these little finite ones, they're all random, so they're all little branching structures. No loops at all, because they're finite. And then we figure out how much they take up, and then 1 minus that will be what's the giant component. But we're going to go straight to the giant component with a physical explanation a little bit. So it's just reprising things. I know it's tricky. So there's just an extra piece that we add, right? So there's a probability that our degree that we choose a node of degree k, And then there's this probability that it's vulnerable. So you just multiply those two together and you get what's the probability that we chose a degree k node that's vulnerable. And then we just construct a generating function from it. Yes?
This is really clear, but I just wanted to...
Really clear, okay.
So we're considering only a finite component of the... I mean...
So this is for infinite networks.
The possibility that it could be, that it could be an infinite collection, that like a giant component that is less giant than a giant component. I mean, that's sort of...
So you mean if you summed up all the finite components, you get an infinite thing? Yeah, right. So,
it's less giant than each giant component. That's sort of a weird thing.
yeah, because it's infinite, there's an infinite, let's say there are nodes by themselves, no friends, right? There's some fraction of the network like that. There's an infinite number of them, actually. But fractionally small.
I mean, that doesn't really matter. I was just curious.
Yeah, one thing we know about random is the blob in them, and this happens over and over again with real networks. There's a blob, and if you have you can't have two infinite components because they would, in the random wiring process, they'd have to be connected.
So it's not a physical thing. Well, it is a physical thing, but it's not mathematically possible, but it's just almost entirely improbable.
It would never happen. It's vastly. It's just yep. I mean, you will just never see it. Yep. All right. So we had to get our what's the chance if we go along an edge and we hit a node that it is vulnerable, and then it is part of a vulnerable component of size k. So that had this recursive story as well, but the first thing to define is just right. That's for the components. This is just what's the degree. So you can get a degree. Yes. Yeah. Okay. So yeah. So it's kpk. This is just the normal friends. Your friends degree k, right? Normal. This is really q sub k. What we call q sub k. Your friends have k friends. This is probably that friend is vulnerable. So we've put these two things together again, and then we're attaching x to the k minus 1 because we're talking about them having k minus 1 other friends. Okay. You can play around with this. I've kind of expanded this a little bit. You can, normally without the vulnerable thing, we actually have this result, right? So this would be away, which is kind of nice. It's slightly different here. We have the normal R generating function on the bottom and the P1 on the top. Okay, that doesn't matter too much. That's what that says. Okay. And then we got to this. This is really, okay, so this is what I just wanted to show you, and then I'll connect it to a physical argument, which has a couple of components to it. All right, so it's a nasty business. This is the first one we solve. The generating function for rho, which again is so rho sub n is the probability you go along an edge that you hit a vulnerable component, finite vulnerable component of size n. So that has this recursive story, which is the generating function here is that you hit a vulnerable node. It has to be vulnerable, right? That's important. And then it has k minus 1, k other friends. Yeah, that's in here. So that's your sample from that distribution. And then you go and roll this one a bunch of times and add them up. And you add 1 for the vulnerable node that you've hit to start with. This is all times, it's not really showing, this is times x to the 0 because there is a chance that first node you hit is not vulnerable. Trickily, it could be not vulnerable and part of a giant component as well. It could. But it's not a finite, right. That's a different thing. So this is times x to the 0, really. We put 1 in here because we're really only interested in what's right, if you put x equals 1 in a generating function, you get the total probability of whatever the thing is. So we can solve for that, and you've done that in a few of your assignments. We can then stick that in here, and we'll get this beast, and 1 minus the probability that you are part of a finite vulnerable component will be the probability you're part of an infinite vulnerable component. All right, so there's a lot to hold on to in getting this to work. I mean, it's a beautiful bit of mathematical machinery, but there's a lot to hold on to. Okay, so we've been through this before, it's painful. So what I want to show you is, okay, we've got to do this one as well. So there's a much simpler story. This is exactly what we just had. But the triggering probability is a different thing. You just say, well, I don't care where I start. So you just choose a node that has degree k, vulnerable or not. You just switch it on. And based on its degree, then you sample from this distribution, add them up, and then add one for yourself. So you always get one for yourself in this case. So you don't have to worry about the first one's vulnerability. Okay, so that's a simple fix. It's a simple change. So in both cases, you put one here, solve for it, and then you just plug it into here to get this answer. And that's the spreading probability, which is good. Or which is really the size of the triggering component. You can use them interchangeably, right? It's the fraction of nodes that are in a triggering component, if you're randomly sampling from nodes, it's the probability that you started off. Okay, so let's get this from a much nicer explanation. All right. So, first of all, we have, I'm going to frame it like this. So we have a possibility and then the probability of spreading. So possibility is one thing to look at to start with. It's just it's a binary indicator, right? It's really, are you in an ice phase or a water phase or a gas phase? It's a good thing to know, right? It's an indicator of phase. And then you want to know things like density or whatever it is in those cases. Here, we just want to know, can they happen or is it impossible? And then if they can happen, what's the probability? Now, obviously, the probability gives you the fact that they're possible or not, fine. But there are different ways to get to those stories, and it's easier to get to just the possibility. It's a different argument. Okay, so we have this story that we have a giant component of vulnerables, if it's possible. So that's just that's the first test, if you like. And then what's the probability that a node will infect it? And we're going to call it p trig. It's the same as the size, the fractional size. And as usual, it's about edges, right? So this is going to be q trig, which is going to be the probability that if we go along an edge, it triggers a giant cascade or a global spreading event. So that's good. We're going to go right into the heart of this thing. We're not going to avoid it and kind of sneak around the giant component. We're just going to say, boom, does this thing light it up or not? And so this is a much easier way to do it. I mean, if you read Duncan's original paper, if you go through it, you'll see that this is the 2002 paper in PNAS on cascades in random networks, and how you have this, all these things we've talked about, robust yet fragile situation. Most individuals look like they're impervious to spreading, right? Their thresholds are not going to be exceeded by just one being on. But the whole thing can explode. It's a very interesting structure. It's the evolution of it's Granovetter's model transposed onto random networks. So it's all generating functions. But you could get to everything in that paper and more with this, and then Gleason stuff comes later on for the final piece. All right, and then you can, and I'll show you this, and I'll just give you a list of what we did. But you can generalize to you can actually much more easily generalize this process to other kinds of random networks, assortative ones, for example. Then the generating function, which I very quickly showed you some slides on, it gets horrific. Okay. Then you have generating functions with subscripts based on the degrees, right? So you'll have an f, k1, k2, and so you have an infinite matrix of generating functions. Okay. It's a little nasty. Okay, so this is pretty simple-minded, right? And I like that. So we're going along an edge, and we want the thing to explode. And, well, let me show you this. All right, so, this is the basic story, right? So you're going to hit a degree k node. Question is, does this lead to a giant component with this spreading mechanism on this network? Well, a couple of pieces, right? So this one has k minus 1 friends, so it's a degree k node, k minus 1 friends. Sometimes it's good to say k or k plus, but here we're doing this one has k friends. So it has k minus 1 other friends. Well, what's the probability that this edge does not lead to a giant cascading event? All of these have to fail. right? And that happens with this probability, 1 minus q to the power of k minus 1. 1 minus q is that the edge does not lead to something, so we're just going to multiply them all together. But we just need at least one of them to get there, right? So, and that at least one of them succeeds as 1 minus that. We could do the kind of ridiculous thing of saying, well, there are k minus 1 choose 1 ways of success, because it's true, right? So we could do that, and then we'd say q, and then we'd have 1 minus q to the power of k minus 2, and then we could say there are k minus 1 choose 2 ways of having 2 of these on, and we'd have a q to the power of 2, and then a 1 minus q to the power of k minus 1 minus 2. So that would be, right, we could do all that. And if we think about that, that really is this. So there's just 2 ways to see it. But this is, right. And then we have to sum over all the degrees, right? So this is pretty good. That's a nice little recursion relation. It's defined in a straightforward way. It says what q is. Q is the thing you're kind of looking for. It's not, the generating function was always like, we're going to get 1 minus the, like we're going to sneak around the back and find it in a kind of a questionable way. Okay. Whoa, what's wrong? Yeah. Two different q's. Ooh. So this one?
Q on the left-hand side.
Yep.
Is equal to a different expression Q on the right-hand side.
Yeah, so this Q, when we say what's probably that this edge leads to a giant cascade, well, we say it's got a, and this is where we don't even have this is where we don't have a contagion mechanism, right? There's nothing about that. This is just saying, I'm going to hit this one, and then it has this degree. It has probably k with this degree. Wow. It has degree k with this probability. And then this is the probability that at least one of the outgoing edges from that goes to a giant component. So this is just about giant components, actually. It's not a cascade thing yet. But we know that you sort of just pull back from that. We really just need to stick in a bk1 here. So you solve for q from this. Yeah. Oh, I'm sorry. Is that good? So what will happen typically is q, it will have some kind of story like this, for example. So right, this is q equals, right, this way. This is just q equals q. Right, this is the y equals x line sort of thing. I kind of hate doing that. I shouldn't do that. And then you've got something maybe that looks like this, whatever it is, in general. There's some story here. Yeah, you could do one of those to find. That's an interesting point. You can actually solve it. You can use it numerically. You could solve it like that. You could use a cobweb thing to do it. Yeah. I mean, it depends. I'm sure I've drawn the wrong thing, but yeah. So you're going to solve it, and if so, that's actually an interesting point, right? So q equals 0. Always satisfies this equation, right? So you put a 0 here, 1 minus 1. So q equals 0 is always a solution. And then the issue is there a non-trivial solution between 0 and 1? Or another solution between 0 and 1. And then what you get is essentially q equals 0 is always a solution, and then there's, let me draw this. It often looks kind of like this. Right, so q equals 1 is always a solution. Madness. And then there's another solution that looks like this. Let's say this is 1 here. And yeah. Am I doing the right thing? This is depending on how you're tuning things. Maybe you're tuning through random networks in some way. And we could be tuning through, random networks. Right, and so this will be a transcritical bifurcation, right? So that the solution you want is here, and then this actually is not a solution. So that's sort of all right. Was there another? Yeah. Yeah, so then here's the, right, so I had this, and then that's it. So then here, that was just for giant components, and then here's the story if you have an actual infection. Everything looks the same, but we stick in, well, I've got B1K, but BK1 in here. All right, so everything looks the same. So this is a much simpler story. Let's fix that up. We must have notation goodness. And then you solve this guy, and then you just put it into here for the probability of triggering, which is, so this is simpler. This is, and I'll have these in the other slides. Okay, you're going to choose a node, has degree k, you switch it on, and then this is the probability that at least one of its friends is on. It leads to a giant component. So you do all the hard work here, and then you switch one on, and then this is the probability that one of its, because this node you choose, k friends, has k random edges going out, right? They're randomly connecting like this. And then we know there's a q probability with them. And so this is probably at least one of them leads to the giant component. So pretty easy to solve, actually. How are we doing? Right, so this should appeal to physically, right? So this is, just stepping through it again, right? This is, and I'm using Q a couple ways, but it's usually just the edge, right? Q is about edges, and R is about edges as well, but Q is going to a degree K node and talking about its degree being K. R sub K was useful in some places. You're going to a degree K plus one node because you're worried about how many edges are going out, K, and that's just easier notationally sometimes, but. Okay, so we have these things. This is the probability that you reach a degree K node. It's infected with this probability. And then this is the story I just wrote up. Okay. And you put everything together, you get this. So this is cool. We're just writing it out, you know. And so this has a physical story to it. And I like to use these bullets to sort of say, this is a piece, this is structure, this is the contagion piece, and then this is a recursion part for the contagion. So you solve it, and you're good. And so it wasn't quite on those notes. So there are two pieces we can then build on. So this is the probability that you are that the node you choose to start with is part of a vulnerable component. And all it has is this extra piece in here. It's got degree K. Then this is the probability that it's vulnerable. And then we have these pieces as well, right? So we have that same structure here. This is probably that at least one of its neighbors traveling through them leads to a giant component of this cascade. And if you look at this essentially says, so again, when Q triggers, when it's 0, this is 0. Make sense? So we need to have this to be at least 0. And then this has some substance. So these two things will kind of collapse for us. And the probability of triggering is a simpler thing. It's all of that, except you don't care about your first one. So you just have the probability that your first one is vulnerable is out of the game, you just infect it. You just switch it on exogenously, right? The underlying degree distribution? Oh, yeah. That's fine. Yes. Yeah. Yes. I know we have some things where we've summed things up to be less than. No, this is a healthy network underneath it, and we're imposing some aspects of the contagion process on top.
Because then the expression for this is really nice. Then P trig is equal to 1 minus the generating function of P evaluated at 1 minus.
Right.
And
it is.
In the way all along, you just get this either this 1 or this mean. You get the first derivative maybe evaluated at 1 minus. It's very.
So let's connect those two things because it's nice to do. It takes a little bit of work. We had this. Not much. We had this result, right? This is the basic thing that you're figuring out with the generating functions. You're trying to find this kind of slightly perverse thing. What's the probability that traveling along an edge leads to a finite vulnerable component, right? Sort of avoiding the issue. But this is the observation. If you set that quantity equal to 1 minus the probability that you're actually going to a giant component and triggering it off, and we put in what this generating function is, and we can just sort of work through this, right? So the left-hand side up here is 1 minus q trig. That piece in there, this blob up here, same thing, it's 1 minus q trig. And we put in the generating function for vulnerable nodes in the R version of it. So we've got the k pk over the average degree, right? That's the connective piece, then this piece. And then this was x to the k minus 1, so it's this blob to the k minus 1. Out the front, there is a small piece here, which is, it's this guy evaluated at 1, right? So we're going to put 1 here, so that's all of this. And then if we look at this, these two pieces can be joined together, which is nice. There is a 1 here, so we can get rid of those guys. They go away. We can put this is just q trig, we'll put the minus sign over here, minus sign here, plus here, and then you combine these two pieces, right? There's really a 1 here. It becomes 1 minus this blob. It's what we had. It's what we had from the physical argument. Right? This is what we had from the physical argument. This is the q trig story for the physical argument. So it can be retrieved, but you wouldn't be going there, right? You don't know that that's where you're going. Right? This is a very meaningful thing. But if you're just doing it mathematically, then it doesn't matter. You might as well put this minus, this guy could be over here. We could add pi to both sides. We don't care, right? Why not? You just make it look pretty. But meaningless. Okay, this is to get the S vulnerable thing, right? We had that blob as well. I'm just going to show you these things. Again, you use this probability that you reach a finite component, a vulnerable component along an edge is 1 minus probability that you reach an infinite one. Stick all of that stuff in here again. It's a similar kind of story. And everything falls apart. And we get back to the thing that we derived from a physical standpoint. So, generating function story, we know where we're trying to get to. We get to it. Yeah. One more, I think. And we have this this is the triggering probability, so it's 1 minus this guy. Same thing, we do the same thing. And you do some messing around, you get to the same piece. Okay, that's fine. But this, you can go directly to this, and you can look at this, and you can understand why it works. Okay. There's one other piece, and it goes right back to the basics of this, the gain ratio story, right? So very simple. I mean, this is the first thing we were able to write down. This is not in the original works, right? This is something from staring at generating functions for a long time and thinking maybe there's an easy way to do this. You come up with this, right? So again, just writing down this gain ratio story. Connect to a degree k node. It has k minus 1 other friends. You infect it with this probability. So as long as the average number of outgoing infections is greater than 1, right? So one edge begets at least one more infected edge on average, then the thing is going to take off exponentially. And it fits in with so many other kinds of explosive things. So we want this to be true. This is again just going to be a little bit of smooshing around. R greater than 1 has to match up with Q trig greater than 0. It really would be great. And it must come from this, right? This is our so we're just going to look at this, analyze this thing a little bit more. You know, the simple thing we noticed before was if you put 0 in here, you get 0, that's good. If you put 1 in here, this disappears. It's not always a solution actually, right? Because it would be if this was 1. If that was 1, then the sum of this is 1, and we'd get 1. So that's healthy. Okay, so when does this have some solution that is, right, this non-trivial thing away from 0? And we must see that must happen around where this is, it has to be when this equals 1. That has to be the threshold for that. You know, this thing is easier to understand. Okay. So we look at what happens as Q trig goes to 0. It's fun to do. Yeah, it's always fun. These are nice little analysis things. Q trig goes to 0. You want to do that? All right, 1 plus x to the alpha. What does that do as x goes towards 0? This is just, just being for small x. Which ridiculously is theta choose 1, whatever theta is. You can have apple choose 1, which is fun. Okay, so you can approach that however you want, but this is what we're doing. We have a microscopic description of the whole process. We can physically get to this possibility of a global spreading event. It's possible, it's not possible, 0, 1 kind of thing. A different derivation gives you the triggering probability, and then a little bit of math connects those two things. So it's good to know which thing you're kind of working on. There are a lot of works where you kind of go back this way, but it's very important to be able to derive this physically if you can. Anyway, this is sort of I see physicists get messed up about this as well, because they become enamored with the math part, which is very important, but you need to be able to get the physics out if you can. So all right, small q trig, we're going to replace that 1 minus q trig to the power of k minus 1 with 1 minus the power to the small thing times the small thing. This is a Taylor expansion, plus something times q trig squared, k minus 1 choose 2. And so we do that, and that's kind of nice. Okay, so a few things will cancel. Let's do that again. These are going to cancel. This is going to become positive, so that should be what happened. This is a nice little Beamer update that I had to work on there. Alt is a very useful thing. Okay, so there's this blob is going to be connected out there, right? All of this is going away. We just have this k minus q trig. Q trig's cancelled. And now we have exactly the condition, right? This is the edge condition. I shouldn't say edge, but this is the cusp of when you have giant global spreading, right? This blob we know has to be greater than 1. This is our gain ratio on the right. That just finds the point. We need to show that it's greater than 1 or smaller than 1, right? We need to understand that. We know it's greater than 1, but we haven't got that yet. So we need to get this inequality. So this is, as we get towards the transition point. You can't just set, one thing we can't do is say, well, it's 0 at the transition point. Because we're following the wrong solution, right? We actually want to follow the solution that comes down towards, that's non-trivial, right? There's a solution where Q is 0. That's not good. That's true for all networks. Okay, so we take the next one. We just take the next guy, this piece here, and just work with that, right? Some more cancellations and things, and we get this. It's what we had before. Now we have this extra correction. It's minus some positive number times the square. Again, with the cancellation, right? So these guys can go away here. There's a 1 here. That's a 1, and this becomes Q trig by itself. And then we've just swapped a few things around. I've put this blob, right, everything that this is connected to, all of this onto the other side, and then put them back over here, which is naughty, I guess. This is our gain ratio. It's 1 plus a positive number. So just as we move away from the phase transition point, we start to get that this gain, the thing we identified as the gain ratio is 1 plus something. So we can see that our condition for spreading has to be that this blob is greater than 1. Right? It could have been something where we went the other way. I mean, we know what it should be. We could have been something where we went the other way. We know it's 1 at the transition point, then we need to see what happens as you move away from it. And it's this, right? So if Q trig is greater than 0, then we have this blob is greater than 1, and that is our gain ratio story. Now, that was a little mess to do that, right? I mean, that was just some math, right? I don't see that there's, maybe I'm wrong. I don't see there's a physical explanation in it, but this is, sorry. I want to go back to this one. Right? We just went from here to here, and we had to, bash around with some algebra. All right, this is, I'm just trying to assuage my soul, I suppose. It's a much better story. Okay, so it's a mathematical connection. But we don't know about gain ratios here. We've just sort of shown this to be consistent. We were hunting for it, right? For some reason, someone said, "Go and get that thing," but we didn't know that we were, hunting otters or whatever it is, stouts or something like that. Okay, so that's good. That's good. All right, I know a little bit of math, but if you come back to this and you need to know about contagion, this is the sort of key basic section, I would say now, is all of this theory, but the fact that these two pieces are physical explanations. The story for them are physical explanations. Generating functions are great, and maybe I went too deep in this class with them, but these are the ones that have understanding really built into them. Generating functions give you extra superpowers, but yeah, okay. All right. Okay, so that's good. And now we can go a little bit bananas in this direction. Because we kind of have this story now, we can get to triggering probabilities for these mixed random networks. And I'll just tell you some results. But these are what we just looked at, right? Q triggering has this self-consistent story that must be true. And then the probability of triggering, well, it's probably you chose a degree k node, and then it's a probability that at least one of its friends leads to, or if you infect in that direction, it will cause a giant cascade. I know I say lots of different words. A global spreading event is a GSE. Okay, we know it's equivalent now to using the spooky things with generating functions, but this is better. So some kinds of calculations are going to be better with generating functions. It's true. If you want to find the size of the third largest component, you might as well use generating functions. And Mathematica and Wolfram. Oh, God. Okay. Okay, but this is good. Physical arguments are good. They're great. If you have them, you got to do them, right? So, and it will allow us to actually generalize in other directions, I would think. I argue. I will state. So I'm just going to give you a list of what happens and when we go through this family of correlate. So we're going to look at mixed, right? So we have undirected networks, we have directed networks, we have mixed versions of those, and then we have correlated ones on top of that. So this is what we just saw, and this is this funny blob here. This really just says, this really stands for, what's the probability that if I follow an edge, I get to a degree k, an undirected node, it's undirected edges, a degree k node. And so this is really kpk divided by the average degree. It's this Franz-Lestrange distribution again, right? But we're just writing in this conditional way because that's useful. And this simply means it doesn't matter where you came from. Because in pure, all right, no assortativity, it doesn't matter where you come from. There's no correlation. But it allows us to just kind of change this simply when we go to correlations. So you'd have, again, these two things. So you have to solve this for Q-trig. It's exactly the same equation, just rewritten slightly. And then you just bung it in here, and you've got your probability of triggering. So it's going to be always these two-step processes. Directed uncorrelated. So let's look at that one. It has some nice little changes. Well, it has an in degree and out degree now, right? And the probability that you're infected, you have some number that are coming in, and you're only paying attention to them, right? You influence these ones, the in degree ones influence you, and so you want one. So this has to be a k sub I. Before it was just really k. This is, again, this conditional probability that you end up at a node with degree ki, ko, and that's fine. And then, again, yes, 1 minus q trig, and this is k out here, right? So this is, you have k sub O is the number of friends that you're influencing, and this bit is the probability that you influence none of them, and then 1 minus that is the probability you influence at least one of them. So you solve for that. Again, it's just one number here between 0 and 1. Stick it in here, and that gives you a triggering probability. And again, you need the out degree here. So you first choose a node, it has some in degree, some out degree, you sum over all those things. This is okay, so it's a small modification. Then you can do this sort of thing, and again, we're not going to go into all the details, but you have this mixed story where, let's try to look at the first one. So now we've got the no correlations, but you have an in degree, an out degree, and an undirected degree as well. So you've got these three, right? You have a vector, which is going to be k sub u, k sub I, k sub o for everyone. Yep? So this is the probability that none of your friends, that this edge leads to a node. Okay, this edge, you're on an edge, it leads to some node. It's an undirected edge. So you're coming on an undirected edge. It could not infect, right? If it's not infected, then, if none of its outgoing edges lead to a giant cascading event, then you get this piece. If none of its outgoing undirected edges, and there's minus one of those, you have to take one off because you've come in on an undirected one, that's this piece. So you want one minus all of that, gives you probably at least one of those led off to a giant cascading event. So it's all the same structure being repeated again and again. Slight difference here is that if you come in on a directed one, you get to test all of the outgoing ones and all of the undirected ones. But this is a conditional, this is the probability that you have an in degree, whatever it is. Yeah, you're coming on an edge, on a directed edge. And then you can put those things together and you get your triggering probability. It's a similar thing. Choose a node. This is the probability that none of its undirected edges lead to a global spreading event. This is the probability that none of its outgoing ones do. And then so one minus that product is probably at least one does. And then boom. Okay, so then you just sort of generalize this. Now we're going to have a slightly different thing. So Q triggering, now it's dependent on degree, right? So that's a bit nastier. So now we have to have sums over, well, it just gets incorporated into the degree. Depends where you came from, okay? Similar thing for the directed, it's very similar business. You now have these correlated pieces appearing for the probabilities. And you get a slightly messier thing for the directed. Look at this nastiness. Yeah. Not quite as, in some ways, yeah. We got some elaborate things for the cascade condition, if you like. But yeah, so this just sort of generalized. Now we just sort of put a K in here and a K. Yeah. Okay. You don't have to worry about that too much. But yeah. All right. So I know that's a lot. But I feel like that was something that needed to be cleaned up in the course, and will be done in a different way in the future. Okay, so this whole section it's a nice generalization of simple random networks, which we've generalized in various ways, right? We've gone to bipartite structures. This is allowed for assortativity, for directed and undirected. Now it's, we've incorporated directed networks completely. Weighted edges, we haven't done that at all, but that's all sitting there. You can get everything with a physical approach, which is very, very important, right? You really can understand how these things work. The idea of a gain ratio exceeding 1, very straightforward. A triggering probability exceeding 0, very straightforward. And you can go on, you can do all sorts of things with random networks, all sorts of things. Clustering is harder, yeah, but we know that sort of thing. You can apply this same kind of story to bipartite affiliation graphs, multi-layer ones, which we have to do. All right. I know that was painful, but I think it was very important. All right. Anyway, so it's all there now. Good. I feel better. Okay, so let me just tell you a little bit about this. We'll talk about it more on Thursday. This is a strange business. Chaotic contagion. A couple of papers that are behind this. Physical Review Letters was one of them. And we call it limited imitation contagion, right? So that you're imitating in this threshold model kind of way. You copy what other people do. But if everyone is doing it, or some fraction is doing it, you switch off because now it's uncool. So it's incorporating a very natural, ridiculous human behavior. So let's set this up. So they're not monotonic, right? So we're going to have these kinds of response functions. And we'll have probabilistic ones and deterministic ones. But the story is, you're looking at your fraction of friends who are on, And we'll even do this in a big mixed soup as well, because that works as well, right? So your fraction, and then some fraction switch on around you that exceeds this lower threshold, and you're on, sure. We'll wear Ugg boots, because we've got to do it now. Like, you're feeling the pressure. But if everyone's doing it, you're a cool person, so you can't do that. That's too much, right? So you switch off. And so there are some nice little games to play with this. It has connections to other kinds of systems, but so I'll show you this a little bit. If you set a half to be to be sort of a barrier here for the lower threshold and the upper threshold, and you allow this lower threshold to be randomly selected between 0 and a half, and the upper threshold to be selected between a half and 1. So imagine you do this, right? Upper threshold, so they can't cross, right? So you have to do something like this. So if you did that and then averaged over all of these response functions, you know what you get. What do you think you get? Temp map. All right. Temp maps are awesome from a chaos point of view. So you can play little games like this where you know really well what the average behavior should be. Temp map is very famous. And you actually get the temp map, because the middle point's always going to be at 1. You get the temp map, you can dial the amplitude up and down, right? So when it's at 1, then what do you get? So for iterates of the thing, the cobweb, you let them run. If you start at 0, stay at 0. And there's a bunch that get you back to 0. Whatever, all these silly things. Some, countable, blah, 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 right? But your little iterate will travel, you'll end up with it uniformly traveling around in the 0 to 1 interval, right? So it's really chaotic, it's a mess. And as you dial it down, you get different kinds of behavior. But it's invariant density, right, which is its long-term distribution of where it exists, is the uniform thing. Okay, so nodes are going to imitate up to a point, and then they don't want to be like everyone else. Okay, so this is our story. We will actually give everyone this threshold, this response function, because you can do that too, right? We'll just give everyone a temp map response function. Now it's probabilistic. Now they're kind of switching on and off. And so this is the ridiculous term that we'll use from physics. This is a quenched model, right? So things are, I know this is awful, but it means it's baked in, right? It's baked in. Polymers, I don't know. There's some weird words floating around from polymers. Plastics, right? It's all about plastics. The Graduate? No. Okay. One word, plastics. So money to be made for physicists. So all these people in combinatorics were like, yeah, I'll do self-avoiding walks for your plastics thing. Sure. Never helped. Anyway, maybe they did. Very, very clever work. Yeah. Okay. So you can have this response function. So if everyone's on, you switch off. If no one else is on, you don't switch, right? You don't switch on. So it has a tiny bit of it, but it's very probabilistic, and you're very you switch on and off. The only time is that you will absolutely turn on is when a half of your friends are on and off. But otherwise, you're fickle. These ones are more robust in their response, and so this is so this is a kind of a game we can play. We'll go from systems that are loose to more and more fixed, and so this is the response function. At the same time, you can go from systems where everyone is just randomly mixing, so that's all very messy and relaxed, to a more and more quenched one where there's a fixed network, and so you're stuck, right? So you have these two your little matrix, right? So we have the mess here, and then quenched. So everyone they get randomly assigned a thing, but it's fixed, right? So you get randomly assigned an up and a down threshold, stays that way. So the most baked in one is everyone has a fixed thing, and they're on a fixed network. Their friends don't change, and it's stuck. And then you would think, well, so it's becoming tighter and tighter and tighter. And in all of these cases, we're going to start the thing off by turning one person on, and then seeing what happens. Poke it with a stick. Wonder how many I can do. Temp map, right? So temp map is good fun. This is a nice little definition. So here you go. So there's just a few things. So this is if you have, right, temp map, as you see, has in general has this amplitude you can dial up and down. Okay. So here we're just dialing the thing up, and it has cobweb, it's escaping, right? This is an unstable fixed point because the slope is manifestly greater than 1, and it takes off, but then it gets stuck here. this sort of thing. And as you dial it further up, right, that's the one we're going to be interested in. This thing just travels all over the place. Well, yeah, I mean, once you've got everyone in a big soup, yeah, then you get more of a. I see. So I see what you mean. Yeah, right. The normal thing is, yeah, it's a system watching itself. Right. There's one thing that cares only about what it did before. We're going to spread it out to everyone's got to. So here, that's a very good point. Here, your system, you've got one thing. It's got a number associated with it, and it updates. So time t+1. Based on what number it is before, it just looks up and it gets its new number. So it's a number between 0 and 1, right? But what we'll have for this is everyone's number is actually 0 or 1, right? They're either on or off. Ugg boots are on, Ugg boots are off, right? 0 or 1, yeah. Oh, this is very nice. So as you look at where this thing travels around as a function of this amplitude, so this is a low amplitude, so R is the amplitude, so it goes up to 2, right? Over here it's 2. Right, so we let this thing run, and you get this very nice, it's actually, it fills it in. It's different to, this is an important thing, it's very different to the logistic map, which you got the t-shirt of probably, right? Yeah, which has, where they're all separated, they're just, they're lines. Yeah, I'll show you that again. So this is, it fills in a compact set. And these are actually pretty tight here, but they merge with each other. And these colors in here indicate how long they spend in these areas, right? So you take a slice here. And so as you get closer and closer to 2, this becomes more and more uniform, and that in fact is uniform at this end. So these are funny little distributions. They kind of have these hops in them. Yeah. But yeah, so you let this one run. So this is maybe, I don't know what that R is. I could figure it out. But it's, yeah. It's going to travel around a fair bit. Okay. Okay. So nodes have limited information. It's a very different game. Instead of one node having a score for itself, a whole bunch of nodes and they're either on or off. Okay, so we're going to have sparse networks and we'll vary the average degree. I know I can't talk about it too much, but I'll tell you a little bit more. Okay, so here's the fun thing. So everyone has a response function like this. If we randomly sample from, this is your lower threshold and your upper threshold, your on and your off threshold. If you randomly sample from this triangle, you get this little thing that looks, it's got a parabolic top, so it's in the logistic map team, right? Universality is pretty huge. As long as you have a parabolic top to this thing, it's all logistic map glory. And if you only say you're going to average like this is what I was saying before, so the first threshold is between 0 and 1/2, the next one is between 1/2 and 1. So you could complicate this in all sorts of ways, right? I mean, this is a uniform distribution here. You could make it uneven. You could do all sorts of things to get some average function that you're interested in. Because we know about the temp map, we might as well try that. So we know how it should behave if everyone's watching everyone else. It should look temp mappy. Okay. Okay, so we're going to do the temp map. Good. Variant densities. Okay, so I'll just show you a few things. We'll see how we do. May have to add some more on Thursday. But, okay, so this is average, so we're just going to look at random networks, right? Which have two flavors, where you randomly rewire every time step, which is, so you can imagine you have a contact. So when you give someone a degree, it's actually the number of samples they take every time step. And they go and sample randomly from everyone else. They still need, if you have degree 5, you still only get 5 samples, right? You ask 5 people, 0, 0, 1, 1, 0, right? And you add that up. So as you make that larger, you're sampling more, you have a better idea of what everyone else is doing. So in this case, it just kind of trucks along, right? The average that's on, the number that's on, that's what this fraction is, this S, doesn't really change that much. And this is, over a long time period, this is the invariant density you end up with, right? So if you chop off the transient and look at where the thing travels around, you get this. Okay, so, sorry. That's the one we just had. This is average degree 5. Average degree 10, now you get 2 fixed points, right? And there's the invariant density. Spends a little more time over here. Well, you'd have to find out the sum underneath that. I shouldn't say that. And then this is z equals 18. It's actually kind of broken, right? Invariant density looks like this. z equals 22. So this has become more and more, you're watching many others, but the thing is it's spreading around. It's kind of jumping around much more. So it sort of might be doing the temp map thing, which is cool. And then this is more and more spread out. This is average degree 30. Okay, let's look at this a little more. So this is, okay, so I should have been a little more clear with this. This is stochastic response functions. So this is a case where everyone has a tent map. Everyone's got a tent map in this case, right? Tent map, everyone has a tent map. So they're all, they're very probabilistic responses. Okay, that's fine. So now if we make a deterministic response function, and this is one network. So we just make the network, it's baked. And then so there's just one network, it's got an average degree of 18, and we're going to start, this is all we're doing as we move between these 6 examples, is starting at a different node. That's all. They have the same response function, which is deterministic, that's fixed, right? So this happens. You get something that looked like what you were getting with the stochastic one, and then it turns off, which is nuts. It collapses. This one collapses, but it collapses into a little bimodal thing, right? It's the same. Everything's the same about this. You just poked it at a different place. Same here. This one lasted, and these are all on the same time scales. This one goes, a lot of steps, and you can see it's almost sort of, it's weird things are happening, and then stuck. This is the average, the fraction that are on. This one just kept going and started to kind of give out this whole thing. What I'm going to get to, and we'll have to come back on Thursday, this is a very strange dynamical system, is what kind of erupted out of this. I mean, we've walked away from social phenomena a good distance by this point, but now it's just like, what is going on with this thing? So this is really weird. Everything is the same, right? Everything's the same. And the usual thing in physics is you poke the thing here and start it off, then random, it's just sort of the transient should figure itself out, and you'll get the same long-term behavior. But that is not happening. So maybe you make higher, you make it more and more connected. And so this is an average degree of 1,000. It's lasting. But look at this. This is an average degree of 100. Average degree of 1,000. This is average degree, I don't know actually. 100, yes, 100 again. This looks like it's just motoring along, and then it has some really weird behavior. All right, so I'm going to connect this to the logistic map in a strange way on Thursday, and I'll talk a little bit about kind of some other things. We'll see. Okay? Okay. All right, so the contagion dosage is almost complete. Now we're into just silliness. Yeah, the dosage has been applied pretty strongly, and in years to come, you can look back at the right place. Okay. Thank you, people.